We are about to present a project we work on at Salesforce, which is making SolrCloud very compatible with public cloud deployments. I am Ilan Ginsberg. I work in search infrastructure at Salesforce for a while now. And Yonik Sili, which is the star, is a Solr creator, one of the founder of LucidWorks, and now also we have the big chance of having him at Salesforce. So the real objective of this work that we are doing is very down to earth. We want to reduce cost to serve because we are doing hosting, and the cheapest it is for us, the better it is for everybody, for our customers and for us. And we want to increase the quality of service, the service we provide to our customers, for the same reasons. The approach we're taking is decorrelating, separating how we do compute, and compute being search and indexing, and how we store the data that we need to query when we index. This works well in our case at Salesforce because we have a data set that we do not use continuously at a known scale, like would be the case for a commerce site selling a catalog of objects that need to be served on all queries. We have a lot of tenants and we do not anticipate how their search behaviors evolves. Data growing, data being accessed or not, etc. So this talk is about changes we are doing to SolrCloud in order to support the separation of compute and storing the actual data. Last year I did a presentation about the same topic on our Salesforce custom cluster, which is not SolrCloud. This time it's about SolrCloud. Really the big picture, like the spoiler of all the rest, because it's easier to put the pieces when you know what you're looking at. Then long section of challenges and how we address things, and are really 2 slides wrap up. So the big picture. This is the single slide. If you fall asleep after this one. We have a Solr cluster, represented only 2 nodes, and a blobstore like S3 or something like this, and a client. And sends an indexing request to a Solr node, which is pretty usual. There is local storage on that Solr node, and the indexing is done locally as usual. Then the data that has been written locally is pushed or written to the blobstore. Once this has happened successfully, and only then does an acknowledgement is sent to the client to tell the client the data has been processed successfully. At some later point in time, for various reasons, another node might be fetching from the blob node that data that is stored there. And when that happens, it allows the client to query either node for load balancing or for load balancing. That's the general idea of everything we do. So if you understand that, I think you're almost done. Some detail. Because we want to reduce the cost to serve, we want to be able to shut down machines. In public cloud, when you do not use a machine, you don't pay for it. We do not want to rely on the storage of that machine being durable. Otherwise, when we shut it down, we lose whatever stored there, and we have to restart the same container with the same storage. So that storage is not durable, and the only durability we have is on the blob side. So just to answer the question from the beginning, reducing cost to serve and improving quality of service. From the customer perspective, improving quality of service means we're going to scale up and add machines when their load increases. And that model makes it pretty easy to add machines. You have the data in the blob store, you put a new machine, and you can load the data that you need to serve. And from the reducing the cost to serve, one aspect is that we can shut down a machine because we know the data is not lost, so we can reduce processing power when it's not needed, like at night, if all your users are in a similar time zone. The other one is that the durability of the data is guaranteed by the blob store. The blob store will maintain multiple copies. So we do not have to maintain multiple copies just for durability. If you were using a block storage, like would be a normal SolrCloud cluster in public cloud, the block storage would be durable as well, but as SolrCloud you would still have to maintain multiple copies. So you will end up using more resources for the same degree of durability. So yeah, that's the presentation. The difference with the HDFS implementation, if you're familiar with that, is that we suggest to share the copy that's on the shared storage. There's only one copy shared by all the nodes that need a given replica of an index. With the HDFS implementation, the storage is remote but is not shared. Each bit of storage on the remote is associated to a single node. And when that node goes down, that remote storage is not used until you restart another incarnation of that node. Challenges that we're going to discuss here is how to control writes. That's the hard problem, because when you have a shared resource, you have to somehow control who can do what. The storage format, what do we put on the blob store? The fact that our nodes are stateless, they can lose their storage when they restart. And then we introduced a new replica type into SolrCloud for implementing that. And there's a lot of things to say about commits. But that's the hard part, that Yannick will be doing this. A few words so everybody understands the problem. SolrCloud is based on leader election, and every shard, every piece of data has multiple copies. One of the copies is considered the leader that is allowed to do writes. So we're looking at two different times for the same cluster. At T1, the node 1, the green one, is the leader. It's receiving indexing batches and it's doing the writes to that index and then pushing it to blobstore. T2, for some reason, the quorum has changed. This node is not part of the quorum at this point in time. Maybe it went into a network outage or big garbage collection. Another leader got elected, and now the other leader, node number 2, is doing the indexing and the writing to blobstore. And this works well in SolrCloud when the storage is individual to each node. But here the storage is shared. So the old leader can wake up and write and overwrite useful data at any time. So we see that leader election does not protect us in the case of writing to a shared resource. I'll come back to this. The storage format. On the blob store, we want to store all the index files. And we do. These are the red blocks on the right side. We give them unique names. We'll see why. And we store a new file that is very simplified on the left, which is a metadata file. And basically it lists all the files for that index that are stored on the blobstore, and the correspondence between the name these files should have on the Solr node and the name under which they are stored on the blobstore. So we see there's like a random suffix on every file name just to make it unique. Basically, this allows us to never overwrite any file on the blobstore. We only write new files. When we have done local indexing on some index and we want to update the blobstore, we compare the commit points we have locally with what the metadata files tells us is available on blob. We are pushing all the files that are missing on blob with new unique names. We are crafting a new metadata file referencing all the files in our current commit point, and we push it to the blob with a new unique name. Now the problem of how we solved the fact that the old leader can come and overwrite stuff. We wanted to make sure that when an update to the blob happens, it does not negates or overrides a previous update that got acknowledged to the client. So this is what happens from the point of view of one update, and all the updates behave in the same way. A client sends an indexing batch, and here we assume, you see the suffix XYZ appearing in all three boxes. We assume that the node has the up-to-date version of the index. An update arrives. The node verifies in a specific Z node in Zookeeper what is the current version in the blob. It happens to already have it, so step 2 can be optimized out, but we are reading what is the current suffix and making sure we are up to date with the blob data. Then we index locally. The node does its normal SolrCloud indexing locally and pushes all the changes, the new files and the new metadata file with a new suffix that's called new suffix. It pushes everything to the blobstore. And that's the important part. It goes to Zookeeper, and it does a conditional update of that tracking field to change from the old XYZ suffix to the new one. And that conditional update relies on nothing else having updated Zookeeper in the meantime. Zookeeper has something with the version numbers to do that trick. And only once Zookeeper has been updated is the new metadata file on the blob considered the latest up-to-date version, and only then we can send an acknowledge to the client saying your batch has been taken into account, it's safe. If you remember the old leader overwriting data indexed by a new leader from a previous slide, if the old leader read an old version of the metadata and then is trying to update it 15 minutes later, it will fail at the conditional update step number 4, and there will be no overwriting of the data written by the other one. I say nodes are stateless. Their storage can disappear when they restart. That means the transaction log is not durable. You can write it, you can read it, but if your node restarts, you cannot read it anymore. And the transaction log are present all over SolrCloud for those familiar with the code. So it's slightly painful. pushing to the blob is the only durability option, and the current way we do it, we push the index files. It means we need to commit. The only way to have durability is doing commit, and this is one of the challenges. In order to implement all this, we've implemented a new replica type that we called shared. This replica type is adapted to what I described. It does not forward indexing because indexing gets to the blobstore and from the blobstore. So the replica, the leader, does not forward the indexing. These replica types know how to push to blob when they're doing indexing and know how to pull from blob when they're doing querying and when they need to pull from blob. As I mentioned earlier, the leader election is not sufficient. I might even say it's not needed. Any best effort leader selection would work because the strategy of guarding the rights to the blobstore would take care of any bad leader choices. That might come as future work. And it forces doing commits. We do not need replicas for durability, but there are some issues of reducing the number of replicas in SolrCloud, namely the way we fail over for queries when a replica is down. So the easy solution is to start with 2 replicas, so failover is immediate when one of the nodes fails. Maybe we can move to 1 replica and have the failure detection become faster, and eventually the goal is to have 0 replicas. We have the data on the blobstore. We do not need to have that data in Zookeeper because we know how to go and see if it exists in the blobstore. And that would be pretty useful for our use case where we can have a lot of tenants and many of them not active at any given time. There's no need to load. And it's almost the same. Having 0 replica means that you load the indexes when you need them. You have a working set that you're really working on. You're not loading everything up front, occupying memory and even disk space for data you're not going to be using, maybe for months. In use cases where multi-tenant, maybe a tenant does not use its data. I think this is my last slide, and I'm going to pass. Yes.
Great, thanks. Okay, yeah, I'm going to be talking a little bit about the indexing performance impacts of Blob. Unfortunately, a lot of this is not necessarily good news. Nothing's for free. So the first thing that might be obvious is that each commit gets more expensive because you have to, like, every time you do a commit, you have to not only flush it to local, now you have to flush it all the way to Blob, and then we do this little conditional write to Zookeeper as well. Now it's a very small write to Zookeeper, but it's still a network round trip. There's also something I'm calling commit amplification, and that just means we're going to have a lot more commits in any system using Blob. Because every update request needs an implicit commit. It needs a push to Blob. And there's also the case that commit amplification causes write amplification as well. And so if you're doing a lot of commits, then you're going to have a lot of small segments. And all those small segments need to be written in the blobstore. And then later they're going to be merged into bigger segments, which again will need to be written in the blobstore. It would have been nice if we just could have started writing with the big segments. But so these extra little segments, that's just write amplification. The total amount of data that's written to S3 or blobstore is going to increase. So when you start thinking about this stuff, you might say, oh yeah, I get it. It's like my data's not safe until I do a commit that pushes to blobstore. So if I just do a commit, then everything I've added before that is safe, right? Unfortunately, that's not the case, and this is a diagram sort of showing why. So we're starting off with our client, and he adds document A, then he's going to add document B, and then he's going to do a commit in separate update requests. And so we start off adding a document, document A, to our leader for shard 1, it's node 1, and then that guy goes down. And then the client, well, before that, we do a new leader election. Node 2 is now the leader for shard 1. Then the client adds document B, and then the client does a commit, which finally pushes to blobstore. So the client, well, he looks unhappy now, and he will be unhappy in the future because every single update request succeeded, and yet we've lost data, right? So he actually doesn't know it yet, but he's going to be unhappy in the future. And so that's really why every single update request requires an implicit commit, and basically some kind of push to blobstore. So how could we go about reducing the commit cost, first of all? We might think about putting the transaction log on blobstore, but that really just exchanges like pushing small segments for pushing small transaction logs. It doesn't really fundamentally change the nature of commit amplification and the problem of just every time, every update request, we need to persist something to blobstore. And it also adds additional complexity because now instead of just managing index versions on the blobstore, now you're managing also like the little transaction logs, and readers have to know how to apply those, things like that. A general thing we can do is increase our concurrency, right? Index with multiple threads, because increasing concurrency can help cover for increases in latency. When one thread is like not doing work, well, if you have more threads, those other threads hopefully still can be doing work. And another future thing we could do is perhaps start writing to blob early to try to lower the latency, right? There's no need to wait for a commit to happen before we can start writing to blobstore. So, could start writing big files early, say. A directory-based implementation in the future may help here too, because then if we're writing a really big file, we don't even have to wait for the whole file to be finished. We can actually start writing it immediately. So the other thing we can do besides reducing the cost of a single commit is try to reduce the number of commits that happen. So one idea is sharing commits. And the idea for sharing commits is if you have multiple indexing packages that are indexing at the same time, they all don't need their own commit if one waits for the other. If they're going to finish at about the same time, then one could wait a little while for the other, and then they could share a commit. And this could be implemented by existing indexing flags that we have. We already have wait flush, and we have commit within. But commit within is currently asynchronous. You just say commit within 5 seconds, and Solr will make sure it happens, but it's not synchronous, which is what we need for the client to know that the data is actually on stable storage. So if we implemented wait flush equals true in conjunction with commit within, then that could do the job of if you have multiple threads indexing, one could sort of wait for another thread to complete a certain amount of time, and then they could share a commit. Of course, this increases latency yet again, and you could compensate again maybe by increasing your concurrency a little bit. A general thing we can do is just increasing batch size, right? So it's like a single update request has to have that implicit commit. Okay, well, add more documents then in a single update request. So increase your batch size if you can. Another idea is perhaps a best effort indexing flag. And what this really means is don't do the implicit commit. Lose data sometimes. Now, this is obviously not a good default, just like we don't know if we saved your data or not. But it might be the right choice in certain really high volume scenarios. But of course, the customer or the client is still going to need a strategy for detecting if they're missing some data and then patching that up later. And then the last thing that I'm going to spend a couple more slides on is client update partitioning. because really the biggest contributor to commit amplification is indexing fan out. So this is a diagram, commit amplification from fan out. So this is really about one big indexing batch that you've sent to try to reduce the number of commits. You send that to SolrJ or to Solr itself, and it gets fanned out to all the shards. And so each one of those sub-requests actually needs its own implicit commit. And so we really didn't do too much by trying to increase our batch size, because the more shards we have, the smaller those batch sizes are going to get again. And it's so this is the number of commits we're going to do is on the order of the number of shards times the number of batches. So it's really not the greatest thing for scalability. It's also the case that each request will get slightly slower as well too, because each request has to wait for the slowest shard. If there's one slow shard, it's going to slow down all update batches. And of course, it causes many small writes to blob, which is just going to increase that write amplification factor as well. So one way that we can try to help out this scenario is to use topology knowledge. And the idea is to line up indexing batches with the actual shards in Solr. And we could use the Solr APIs to get the sharding information, get the hash range for each of the shards, and then do the hashing on the client side the same way that Solr would, and just make batches that don't cross shards. It's also like useful to a lot of the work that you have to do with like hashing and making batches. A lot of times people have to do this anyway to prevent if you do document updates, you want to prevent reordering versions of the same document, right? You don't want to like add document A version 1 on a different thread than document A version 2, because you don't get control over which one hits the index first, and then you can get version reorders. And of course, if you're using custom sharding, then this is pretty easy. Then you should already know the shard names and just make the batches line up with the shards to begin with. But there's another strategy that's kind of related to the previous one. It's actually more of a subset, but it's kind of simpler. And that is to use just the hashing algorithm from Solr and don't worry about the topology. So this, the idea here, though, is that what you do need is to sort of to know how much data that you're going to be indexing to make this effective. And the idea is to scale the number of partitions with the amount of data that you need to index. So in this case, on the left, we only have enough data to create 2 indexing batches. And so we partition the hash space into 2 parts. And so the left batch just has the left half of the hash ring, and the right batch has the right half of the hash ring, or the upper part. And as you can see, when it gets sent to SolrJ now, it hits half the number of shards, or half of the shards, essentially. Now, it is possible that the 2 batches could still collide on the middle shard, but that would just be a little bit more write amplification. And there may be some clever ways that you can normally avoid that too. If we normally split our shards exactly in half, then if we pick a power of 2 for the number of partitions that we create, I think that'll normally prevent any sort of little misalignments and overlaps like that that'll cause a little extra amplification. So in this use case, or this specific case here, is an example of under partitioning. We don't have enough data to create a ton of partitions. We only have 2 partitions, and we have more shards than partitions. But there's really no harm in that, even though there's some fan out, just because like trying to create more partitions, that's essentially doing the fan out anyway. Somebody has to fan it out. It'll still be the same number of commits. So this is the same strategy, but just showing the opposite case when we have a lot of data. So we've created a lot of partitions to break our data up into, but we don't have a lot of shards. So same thing, there's no harm in this case either. In fact, it can be a benefit it's a natural, these channels are natural units of parallelism, and so it can increase your parallelism. So like, the first couple of batches can hit the same shard. That's fine. That'll increase your throughput and help like actually cover some of the latencies from commit as well. And if you do want to set like a cap on parallelism, then you can just keep the same number of partitions and just reduce the number of indexing threads you use to index those partitions. All right, so this is about hash partitioning, doing the hash partition strategy with composite IDs. It's also applicable if you don't use composite IDs. You just like pretend that you essentially have one prefix. So just as a refresher, what a composite ID is, it's basically a prefix on the ID. So for example, Yannick Bang email 1, that would like sort of like squish all of the documents sharing a prefix into the same slice of the hash ring, so that when you query it, you don't have to like query all of the shards. Also point out, this is actually not blob related, but there's a new split by prefix flag for shard splitting in Solr 8.3 that's sort of aware of these prefixes, and so it can like pick a smart place to split shards if you're using a bunch of prefixes. So what you want to do in general for this strategy is first determine the amount of data that you need to index for a collection over some given amount of time period. And if it's a small amount of data, just send it. Don't do the fan out early, because maybe this collection just resides on a single shard right now, and so then you would be causing commit amplification. If it's a large amount of data, then you want to look at the different prefixes and say, which ones are large, which ones are small. If you have a bunch of tiny prefixes that are less than a batch size, just send them all together. If you have medium prefixes on the order of a batch size or two, you might think about using that as its own partition. And then for large prefixes, you want to create multiple partitions by splitting up the prefix for that, splitting up the range for that prefix into multiple parts. And maybe pick the number of partitions to be a power of 2. You can play around with that, see how it works. And then you just go about indexing those partitions with any number of threads that are less than or equal to the number of partitions. Also keep in mind though, if you have many more partitions than indexing threads, you might not want to pick partitions that are right next to each other to index concurrently, because those partitions might all be going to the same shard, and other shards would just sit there idle, so it's just not good for resource utilization. The other thing you want to watch out for is have a strategy of how you're going to change partitioning strategies on the fly. Because again, if you're dealing with updating documents, if you've decided that like, oh, document A goes in this partition, and then indexing continues along and you want to change your partitioning strategy with more partitions or something, now all of a sudden document A might go in this partition, but then this partition might get indexed faster, and then again you've reordered your document A versions. Okay, just switching gears a little bit, just talking about how we're going to handle shard splits with blob. It's pretty much the same way. We can do it pretty much the same way as we do with normal SolrCloud without blob. In this case, we don't have to really do anything too differently, because SolrCloud does not rely on having multiple replicas for shard splitting to work. Because it really relies on, if a subshard leader dies, then the split fails and it has to be retried. And so we can use the same strategy of doing blob. And so updates will be being forwarded. This is the one case where we do forward updates. Updates will be forwarded from the shard leader to subshard leaders. They're buffered by the transaction log in the meantime while the split's actually happening, and then we do the transaction log replay, and then the new shards go active. All right, and now I'll hand it back to Alon for the wrap-up.
Yep, thanks. So elasticity was the initial goal of this project, and we kind of discovered along the way that as we move to the cloud, just the cost of maintaining a number of replicas will be lower with this blob solution, which would not have been the case on a non-cloud environment, because then you're talking about hard disks, and whether you have 3 copies on 3 SolrCloud nodes or 3 copies for blob implementation, it's kind of equivalent, but in public cloud it's different. So there are 2 benefits. And all the approach of considering only the blob as the persistent space allows to shut down servers at any time. And that really allows for an easy elasticity. There's no need to vacate a node or to start all its replicas elsewhere before it can be shut down. Just a closing word. The previous version of this blob work has been used on test environment with production traffic in the past. This work with the SolrCloud version, not yet, but it is planned very soon. We haven't implemented everything we talked about. For example, the replicas, we are 2 replicas. The goal is to contribute this back to open source, and hopefully, if the community likes it, to merge it back into the normal SolrCloud master code base. In the meantime, we are not ready for this yet. We've made that code available as a pull request. That pull request is not meant to be merged, but is meant to be accessible to you, and to comment, to see the direction we're taking. So that's it.
Maybe?
Yes?
Can you talk a little bit about visibility and is there still any kind of software and open systems? What's the impact there?
Did you understand the question? If so, can you repeat it?
I think, yeah, the question was about like visibility and the impact of things like soft commits. That should, it's pretty much unrelated. I mean, the biggest thing to realize that just every update request needs that implicit commit. You don't always have to open a new searcher. You can, we have flags for that too. You know, we have like open searcher equals false. So it's, you don't have to open a new view of the searcher every time we need that implicit commit and push to blobstore. Yes?
Your architecture seems to be oriented around like getting Solr first and then moving into durable storage. Why did you choose instead of going to durable then Solr?
So one reason is what we store in the durable storage now is generated by Solr. So we need a Solr step. Otherwise, if we wanted to hit durable storage first, we would have to send just the documents. The other reason, more pragmatic, is that we wanted to take the easiest path using SolrCloud as it is today. I think there are possible evolutions for the future of that. I think we'll always have to have at least a Lucene step to create the data structures that we want to make searchable. But we might not have to go through the actual cluster and follow the actual sharding strategy. Maybe next year we'll talk about this, I'm not sure.
Okay, I think we are over our time. There is another session starting in here in 9 minutes. I'll hang out a little bit outside if anybody has other questions. And
Yeah. And I will be at the Salesforce booth, so you can come talk.